Welcome back. In the previous video, we walked through all of the circuitry on the playfield board. At this point, I think I know pretty much all I need to know about how the microcontroller controls the features of this board. What I'm missing, though, is how this microcontroller tells this controller in the Backbox how to manipulate the score digits and control its LEDs. So in this video, I want to tackle the SPI interface that the microcontroller uses to communicate with the Backbox over this ribbon cable. SPI is a serial bus used in embedded systems to transfer data. On the bus, there's one master and one or more slaves. In this machine, there's only one slave, and it's the Newton controller that's in the Backbox. The master is the microcontroller on the playfield. SPI typically uses 4 wires. The MOSI pin is used by the master to send data to the slave. The slave, in turn, uses the MISO pin to send data back to the master. These 2 pins' names stand for master out, slave in, and master in, slave out. The master uses this clock pin to tell the slave when to send data or when to receive data. Every transition of the clock, one more bit gets shifted from the master to the slave and from the slave to the master. If there are multiple slaves, the master can use the chip select pin to tell the slaves which slave it's talking to. In this machine, it looks like the slave doesn't do any talking. So we have the MOSI pin that the playfield uses to talk to the Backbox, but the Backbox doesn't say anything back. So there is no MISO pin. There's only one slave, but there's still a chip select. Sometimes, even when there aren't multiple slaves, the slave devices need the chip select to transition between high and low to begin their operations. We'll see if that's the case on this one. I think if I wire the 2 boards together, I might be able to tap into the pins right here and use a microcontroller like an Arduino to output the data that's going across them. Then maybe I can figure out how the microcontroller is telling the Backbox to display different scores and to turn on and off LEDs. The boards are normally powered through this connector using batteries in this battery holder. But for convenience sake, I'd rather power everything off my benchtop power supply. So the first step to getting it powered on the bench is to figure out how much voltage to give it. It runs on 3 C batteries, and they're each 1.5 volts. So I'd expect that it's running off of about 4.5 volts. But I just want to make sure. Yeah, 4.7. These are new batteries. So I want to set my power supply at 4.5 volts and hook it into the same connectors, same pins that this connector would connect to on the playfield board. We can set the Backbox board aside for a bit. It gets its power from the playfield board, so as soon as we get the playfield powered up, it should come up with it. So the playfield board is powered on this connector here. The power comes from the battery holder over the red and black wires there. Those correspond to the B plus and B minus pins on this connector. And we know from the previous video that when the power switch is turned on, this ground pin is connected to the B minus connector, completing the circuit for the playfield circuit board. So we have to get power from the bench supply to these pins, B plus and B minus. If you look at the back of the connector, the pins are exposed, and I can use these little grabbers to make a pretty sturdy connection to them. There's B plus. And B minus. I'll use a breadboard as a convenient way to plug those grabbers into my power supply. Now I've got battery plus and battery minus hooked up to my power supply, and the one connection I'm missing is tying ground to battery minus. I think I'll tap into the ground connector on the top here using a different grabber. And then we can tie that straight to ground here. I'll pull the positive lead out for a second so I can set the voltage. It's 4.5. And now the machine has power. But if you remember, it didn't actually do anything until we activated the start button. So the start button plugs in right there. If I disconnect those two pins with a metal screwdriver. Oh, there we go. Now the board is powered up. So at this point we should be able to hook the Backbox back up to the playfield and see that SPI bus in action. I'm going to pull power first. I'll plug this connector back in. My ground wire fell off. This isn't going to be too stable, I don't think. It will connect underneath. Alright. apply power and see what we can see. Hey, there we go. So my goal is going to be to tap into the SPI pins there while the microcontroller is communicating with the backbox, and maybe activate some switches and get this score to change and see if I can see, well, number one, see if I can see any data on that MOSI pin, and then see if I can see the data changing when I activate switches and get the score digits to change. Now that I've got the board powered up, I want to do a little bit of poking around just to verify some of my assumptions. Let's check the voltage that this is running at. So we're outputting 4.5 volts from the batteries. It is 3.5 volts at the micro. I was thinking maybe 4.5 might be enough to run a 5-volt micro, but the regulator is putting out 3.5, and the reason that's interesting to me is because all of the microcontrollers I have, I've got a handful of Arduinos and a Mega, and even the basic stamp that I used in my getaway tachometer videos. All of my micros are 5 volts. So I can't just drop any of the microcontrollers that I have in place of this one, because all of mine need 5 volts to run. They're not going to run off of 3.5. So I'll have to figure that out later. I'll have to get a hold of a 3.3 volt micro that I can use in place of the one that's on this board. I spent a good amount of time in the previous video trying to figure out how these optos worked, so I want to see if I got that right. I'm going to hook up my ground to the ground of the whole system there, and then take a look at what I identified as the sense pin on sensor number 1 up here. So this top solder pad, I was expecting it to be high when the beam wasn't broken and low when it is broken. So let's take, oh, there we go. So it's low or it's high, low. Oh, this screwdriver is maybe too small. Low if it's broken, high if it's not, low if it's broken, high if it's not. Nice. Next I want to take a look at the SPI on this ribbon cable here, and to do that I'm going to ditch the multimeter and use a logic probe instead, because if I were to put the multimeter on the MOSI pin, for instance, my theory is that that's oscillating really quickly, so I'll see some voltage on it, but it's going to be hard to tell if it's just like I'm expecting it to be like kind of in the middle. It'll be less than 3.5 and more than 0. And the multimeter is not fast enough to show the oscillation, so I'm hoping that this logic probe can show me that indeed there's some binary data going across that and it's oscillating very quickly. I'm going to get that hooked up. I'll be right back. Okay, all hooked up. So the probe has 3 connections. There's the positive voltage of the unit that you're trying to test, which I've got hooked up to the VCC lead next to the SPI bus. Then there's the ground connection of the unit that you're trying to test, which I've got connected to the main battery ground. And then on the probe itself, this is where you place, this is the probe that the lead that you place on the trace that you're trying to test. So the probe will show you whether the signal is logic level high or low, and this light will flash if it's pulsing. And it'll also make tones that correspond to the frequency of the pulsing and in general how high or how low things are. So let's fire it up. And we'll just take a look at signals that I know are high and I know are low. So we'll look at VCC and ground on the micro. So of course VCC is high, and ground is going to be low. Now let's take a look at these SPI signals. I'm going to do chip select first. So it's pulsing maybe slowly. It's interesting that that's pulsing to me. So chip select is used when you have multiple slave devices in a circuit being controlled by a single master. The master has one chip select trace going to each of the slaves, and the slave that it wants to talk to, that it wants to command, it will set the chip select low. So I was kind of expecting this chip select to always be low, since it's only talking to one slave, but it looks like it's pulsing. Let's do clock next. Pulsing maybe faster. And now the one I'm interested in, MOSI. So this should be the binary signal going to the backbox. Oh, that's interesting. Maybe it's changing. Oh yeah. So watch the bonus LEDs. Those kind of change with time. Every 6 seconds those bonus LEDs are going to change. And every 6 seconds you'll hear the tone change. So those LEDs are actually controlled by the backbox. I bet some bits are changing. We lost power because it timed out. And it looks like that MOSI pin goes high when we lose power. Let's bring it back. Yeah, as these LEDs change, the tone changes. That means, I'm guessing that the bits on the SPI bus are changing. And that's causing the logic probe to sound a bit different. Interesting. Next, what I want to do is get my Arduino hooked up on the SPI bus. Now that might be a little bit tricky because this Arduino runs on 5 volts. And it's important that the master and slave have the same voltage reference, so they have to share a common ground. So I can't power this board and the Arduino from separate power supplies. I have to power them from the same source. This micro is running at 3.5, and this one needs to run at 5. Now, luckily, the battery power that I'm getting, I was measuring 4.7. Recently I've been powering the board off of 4.5, but I could raise it to 4.7, just like I was getting from my fresh C batteries. Count on this regulator to drop it to 3.5 for this micro, and then hope that this runs on 4.7. It probably would. Or I can actually use a diode. If let's pull this off, I'm done with that. I was using that diode as just a convenient place to hook my logic probe, but if I were to string this diode off of my positive battery voltage, which I'm sending 4.7 here now, I could set this at 5 and count on the voltage drop of this diode to lower it to, it'll lower by about 0.6 volts, I think. So if this was 5, this drops it by 0.6, I would get 4.3 out of here, which should be enough for this regulator to function. And then I could hook my Arduino straight up to the 5 volts ahead of the diode, and then run both of them, both this board and the Arduino, off a common ground. That would give them both the same voltage reference. I think I might try that. Let me show you what I'm talking about here. Bring this guy back. We'll put the meter on common ground here. Fire this up. We'll put it on 5 volts because that's what the Arduino wants. And if I measure at the voltage source, I've got a good 5 volts. If I measure at the diode, 4.8. So I would think that's good for that regulator. So good for the Arduino and good for the regulator. Alright, so let's get that hooked up. I'm going to set my voltage output to 5 volts because that's what the Arduino needs. And hook up the playfield PCB past the diode, so it should be getting a voltage that it expects from a typical set of batteries. Can power that up to make sure it's running. Alright. Now let's get the Arduino powered up. I'm going to hook its ground connection to a common ground point. That's what is important for the SPI bus. plug that directly into one of these ground pins. Then you can power the Arduino several ways via the 5-volt USB port or the barrel jack, typically 9 or 12 volts, or this 5-volt pin, or the VN pin. VN is connected to the barrel jack, so that is expected to be a higher voltage that goes through the regulator, the 5-volt regulator that powers the Arduino. The 5-volt connection here is the output of the regulator, which is tied to the 5-volt USB. So I can power the Arduino directly off of the 5 volts here prior to the diode, and I'll hook that into the 5-volt pin. There we go. So you can see it's powered on. Let's test to make sure, yep, that powers on too, so we're good to go. One thing to be careful of if you're powering an Arduino directly off of regulated 5 volts using the 5-volt pin is that you don't want to connect voltage on this 5-volt pin and also connect your USB, because at that point you've got competing power sources. It's not good for your Arduino, and it's probably not good for whatever is powering your USB, especially if that's a PC and you're trying to make a serial connection to load new software on your Arduino. So when I go to program this, I'm going to have to remember to disconnect this 5-volt connection before I plug in my USB.
The Arduino has built-in hardware SPI capability. It uses pins 10 through 13. We'll be using the chip select on pin 10, master out slave in on pin 11, and the clock on pin 13.
I've got an Arduino hooked up to the playfield. Pins 10 through 13, like we saw in the diagram, are tapped into the SPI bus on the playfield. Even though the microcontroller on the playfield is running at 3.3 volts, I'm hoping that the 5-volt Arduino will still be able to see the SPI communications. It's got a threshold voltage where any voltage above a certain value is considered a binary 1. And I'm hoping that even though the 3.3 volt microcontroller is not putting out a 5-volt value for logic high, I'm hoping that the 3.3 volts that's putting out is above the Arduino's threshold for what it considers to be a logic high. So we should be able to see the 1s and 0s that are coming out of the SPI bus. I've changed the way the system is powered. You can see I've got USB plugged in. This is going to my PC. I don't have a power supply connected to the breadboard anymore. In fact, the breadboard and the playfield and the backbox are all being powered through the USB connection to my PC. I have to have this USB plugged in so I can see the serial output of the Arduino when it's reading the SPI bus. And you don't want to have external power plugged in at the same time that you've got USB plugged in, or you could fry the Arduino. So the USB connection to my PC, the maximum current, is definitely enough to carry both the Arduino and the pinball machine's playfield and backbox.
I wrote an Arduino sketch that opens an SPI connection and dumps the data out over the serial monitor. It has the same two functions that you normally find in an Arduino sketch: setup, where we initialize everything, and loop, where we do the work. It also has a couple other functions. To bin and to hex, take a binary byte and write it out in either binary or hexadecimal. And something that's SPI specific is this interrupt service routine that gets called whenever a new SPI byte comes in over the bus. In the setup routine, I initialize the serial monitor connection and set up the SPI connection. All of the SPI pins are set to inputs. And then I initialize the SPI control register. This web page has some information on the control register, but there are 8 different bits that control how the SPI connection is made. These 2 bits control the speed, and I'm not sure it's even relevant for a slave-only operation. But I went ahead and set it to the maximum speed. SPI has a few different modes. If you're using the Arduino libraries, these modes are set using an enumeration. But the Arduino library doesn't handle slave operation, only master. So for my slave operation, I have to set these modes myself. So there are 4 different states. And I think I just got lucky by setting these values both to 0. It's the default. The next bit controls slave or master mode, so I'm set to slave. I'm expecting data to be written most significant bit first. Then you enable the SPI hardware and enable the SPI interrupt. This is the SPI interrupt. This gets called anytime a new SPI byte arrives over the bus. So in this sketch, I'm just writing it to a buffer. What I found in reading this data is that it's coming way too fast for me to output the data at the same time that I'm receiving it. So I just set up a relatively large buffer, well, large for Arduino standards, a relatively large buffer. And then I read data over the SPI bus and dump it to that buffer until the buffer fills up. Then after the buffer fills up, I signal to the loop thread that it's time to dump the data from the buffer to the screen. So the loop thread waits for that signal and then goes through the entire buffer and prints it out to the screen. So while that's happening, the SPI interrupt is just dropping data because I don't want to write to that array while the loop is writing it to the screen. Otherwise I'd just get gibberish. So it ends up that I'm receiving chunks of data, then dropping data while I write to the screen, and then I go back again to receive chunks of data. I was trying to read and write at the same time in the first sketch that I wrote for this, but no matter what I did, I couldn't keep up because my serial connection, where I was writing the data to the screen, wasn't fast enough to write data as it was being received. So I ended up losing a lot of data, and it made it hard to analyze it.
So let's go ahead and start the board and see what data we get on the SPI connection. So lots of bits. So what we're looking for is repeated patterns. I wasn't quite sure when I started pulling this data if it was going to be even byte aligned or if it was just bit aligned. So that's why I have a mode where I can dump things in binary like I'm doing now. I can change the sketch to show hex. Sometimes it's easier to see patterns that way, although it looks pretty easy right now to see the pattern. We'll wait for this output to stop. There we go. So we can see CO 81 7E seems to repeat. So that's the first, second, third bytes of what looks to be a frame, and they both end in 0990. So that's 1, 2, 3, 4, 5, 6, 7, 8 bytes. When I first started dumping this data, I was losing all kinds of bits because I was trying to write it at the same time. It was really hard to figure out what the pattern was. It looks easy now, but I've had to figure out how to write this sketch so I don't lose any data. So I've got this value up here that allows me to set the number of bytes in the frame. I'm going to set that to 8. And let's go back to writing it in binary. And we'll start the board up again. You might see these bits kind of shift around. I'm not doing any kind of processing to make sure that the frame always starts with this byte, these 2 bytes. So you might see it move around a little bit. We can start a game by shooting the ball by interrupting these sensors. And you can see how the bits change. So I can score by interrupting the scoop sensor back here. And you can see some of the bits change as the score changes. So we're definitely getting good data across the bus. Now remember that those bits are not in real time. I'm grabbing a K, 1024 bytes, and then I'm spending time writing it to the screen, dropping data while I'm doing that, and then grabbing another K, and then dropping data while I'm writing it. So there's lapses in the bytes. But just being able to manipulate the score like this was enough to kind of figure out what's going on here.
I spent weeks poring over output like this, trying to figure out how the micro was communicating score and LEDs to the backbox. And I could tell just by varying the score by closing switches on the playfield and increasing the score that it had something to do with these bits. But I couldn't really figure out how the micro was communicating the score digits. I noticed that these bits always had this pattern where there was a 1 here, then here, then here, then here, then here, then here, and then it repeated. That seemed to always be the case. And I could tell that sometimes bits like this changed, and that seemed to correspond with LEDs being lit or not lit on the playfield. But mainly what I was trying to figure out is these score digits. I could not figure them out. So after a while, I I just like thought, well, I'll put as many scores as I can on the same, screen and see if I can see any patterns. So this column A is a bunch of different scores that I queued up on the machine, increasing from 0 all the way to I sat there for a long time hitting switches to get that score. And I grabbed. I said earlier that these bits had a pattern like this. It seemed to repeat. So I grabbed a section of the data for each score. But I could not figure out how like this score was captured in these bits, because it wasn't anywhere else. Like nothing else changed with the score except for these bits. So I was like, I broke this down into binary. I knew with 6 score digits that it would take 1, 2, 2.5 bytes to store that data. So I was looking for, was there somewhere that I could shove 3 bytes in or 2.5 bytes in? And I thought, well, maybe the score is like, maybe it's always even because the bonus is awarded as 2% of your total score. Can I get an odd score? I don't know. Maybe it just shoves it to even because like all these scores were even. So maybe I don't need that last bit. But still, no matter like how I tried to reason it, I couldn't fit all the score digits into these bits. And I especially looked at a score of all zeros. So a score of 0 is all 0 bits, and I was trying to fathom how that is 0. So I tried to apply like a bit mask to it and try to find a mask that worked for zeros and also worked for hundreds. I was like just stuck trying to fit these bits into here. I think mostly because of my background in software. I was trying to figure out, as a software engineer, how do I fit this pretty large binary number into just that many bits? But it was kind of my background as a software engineer that betrayed me a little bit here, because it turns out they're not communicating, the micro is not communicating this number to the backbox. It's communicating the state of the LEDs on the scoreboard. What finally tipped me off was looking here and seeing that there's 1, 2, 3, 4, 5, 6 different lines to communicate the whole score. And I was like, and then also I noticed that this last bit was always 0. So they were communicating the score using only 7 bits. And I was like, 6 lines, 7 bits. And then I thought, oh, it's maybe there's 1 per score digit because there's 6 digits and 7 bits. I'm working with 7 segment displays. And that's what it ended up being. That's the pattern that finally worked for all of these different scores. It turns out it's like this. So you've got bit 1 through bit 7, and they correspond to each of the 7 segments in the 7 segment display. And there's 6 digits, 6 7 segment displays in the score display. So for instance, when the display is showing all zeros, 6 zeros, the micro is telling the backbox, turn on 1, turn on displays 2, 3, 4, 5, 6, and 7. So that's 2, 3, 4, 5, 6, and 7 on, making a 0. And if we go down here, what really tipped me off was I was trying to figure out how, when I transitioned from all zeros to all zeros with 1 1 and all zeros again with 1 1, I thought, this in no way makes 100 when this is 1,000. And then I was like, oh wait, it's this digit and the rest are all zeros, and then it's this digit and the rest are all zeros, just like up here. Anyway, so let's find if we want to make number 3, then we're looking at the lowest numbers are 4 and 4, and then a 3, and then a 4 again, just like these up here, and then a 6 and a 3. So we want segments 1, 4, 5, 6, and 7. 1, 4, 5, 6, and 7. Making a number 3. And that is really exciting for me because it looks like I don't have to just throw numbers up there. I've got direct control over each of the segments. So I can do cool stuff with like alphabetic characters, like here, and I can do patterns, like the old like System 11 alphanumeric games from Williams. So I've got direct control over each of the 6 7-segment displays, and I've got direct control over each of the 7 segments in each one of them. That's pretty sweet. And I think I can do a lot more with that than what the stock software does. I'm pretty excited about that one.
Alright, my plan is to find a microcontroller that runs off of 3.3 volts, that has enough pins to mimic the interface of this one, and also that can produce audio as nicely as this one does. Then maybe I can hook it up in place of this controller and get it to display score and control the LEDs on both of these boards. That'll have to wait for the next video though. See you then.